I am Ivan Michael Siachensa of Batangas State University, Bachelor of Science Information Technology from the section IT 102. For this video, I'll be doing the summary of Chapter 5 titled The Ethernet, and this is in CCNA, Routing and Switching. So let's start. Ethernet is now the predominant LAN technology in the world. Ethernet operates in data link layer and the physical layer. The Ethernet protocol standards define many aspects of network communication, including frame format, frame size, timing, and encoding. When messages are sent between hosts on an Ethernet network, the host format the message into frame layout that is specified by the standards. This chapter examines the characteristics of operation of Ethernet as it has evolved from a shared media convention-based data communication technology to today's high-bandwidth full duplex technology. Ethernet encapsulation. Ethernet operates in the data link layer and physical layer. It is a family of networking technologies that are defined in the IEEE 802.2 and 802.02.3 standards. Ethernet supports data bandwidths of. So here are the Ethernet supports data bandwidths. The Ethernet LLC sublayer handles the communication between the upper layers and the lower layers. This is typically between the networking software and the device hardware. LLC sublayer takes the network protocol data, which is typically an IPv4 packet, and adds control information to help deliver the packet to the destination node. LLC is used to communicate with the upper layers of the application and transition of the packet to the lower layers for delivery. MAC sublayer. MAC constitutes the lower sublayer of the data link layer. MAC is implemented by hardware, typically in the computer NIC, and specifics that are listed in IEEE 802.3 standards. Data encapsulation. The data encapsulation process includes a frame assembly before transmission and frame disassembly upon the reception of a frame. In forming the frame, the MAC layer adds a header and trailer to the networking layer PDU. Data encapsulation provides three primary functions. Frame delimiting. The framing process provides important delimiters that are used to identify a group of bits and make up a frame. Addressing. The encapsulation process contains the layer 3 PDU and also provides for data link layer addressing. Error detection. Each frame contains a trailer used to detect any errors in transmissions. Media access control. Control responsibility of MAC sublayer is media access control. Media access control is responsible for the placement of frames on the media and removal of frames from the media. Ethernet frame fields. The minimum Ethernet frame size is 64 bytes and the maximum is 1518 bytes. This includes all bytes from the destination MAC address field to frame check sequence. MAC address and hexadecimal. An Ethernet MAC address is a 48-bit binary value expressed as 12 hexadecimal digits. Just as decimal is a base 10 number system, hexadecimal is a base 16 system. The base 16 number system uses the numbers 0 to 9 and the letters A to F. Given that 8 bits, 1 byte is a common binary grouping, binary 000 to 11111 can be represented in hexadecimal as a range 00 to FF. It is important to distinguish hexadecimal values from decimal values regarding the characters 0 to 9, as hexadecimal is usually represented in text by the value preceded by 0x or a subscript 16. Less commonly, it may be followed by an H, for example, 73H. However, because subscript text is not recognized in command line or programming environments, the technical representation hexadecimal is preceded with 0x. Hexadecimal is used to represent Ethernet MAC addresses and IP version 6 addresses. Hexadecimal conversions. Number conversions between decimal and hexadecimal values are straightforward, but quickly dividing or multiplying by 16 is not always convenient. If such conversions are required, it is usually easier to convert decimal to hexadecimal value to binary and then to convert binary value to either decimal or hexadecimal as appropriate. MAC address Ethernet identity. Ethernet, every network device is connected to the same shared media. Ethernet was once predominantly a half-duplex topology using a multi-access bus or later Ethernet hubs. MAC address representation. Windows hosts the IP config. All command can be used to identify MAC address in the Ethernet adapter. Unicast MAC address. A unicast MAC address is unique address used when a frame is sent to a single transmitting device to a single destination device. The process of a source host uses to determine the destination MAC address is known as address resolution protocol. Although the destination MAC address can be unicast, broadcast, or multicast addresses, the source MAC address must always be a unicast. A broadcast MAC address. A broadcast packet contains a destination IPv4 address that has all ones in the host portion. This numbering in the address means that all hosts on the local network will receive and process the packet. Many network protocols such as DHCP and ARP use broadcast. Multicast MAC address. Multicast addresses allow the source device send a packet to a group of devices. Devices that belong to a multicast group are assigned a multicast group IP address. The range of IPv4 multicast addresses is 224.0.0.0 to 239.255.255.255. Switch fundamentals. A layer 2 Ethernet switch uses MAC address to make forwarding decisions. It is completely unaware of the protocol being carried in the data portion of the frame, such as IPv4 packet. Unlike legacy Ethernet hubs, it repeats bits out of all ports except the incoming port. An Ethernet switch consults a MAC address table to make a forwarding decision for each frame. Filtering frames. As a switch receives frames from different devices, it is able to populate its MAC address table by examining the source MAC address of every frame. Cut-through switching. In cut-through switching, the switch acts upon the data as soon as it received. Even if the transmission is not complete, the switch buffers just enough of the frame to read the destination MAC address so that it can determine to which port to forward the data. There are two variants of cut-through switching. Fast-forward switching. Fast-forward switching offers the lowest level of latency. Fast-forward switching immediately forwards a packet after reading a destination address. Fragment-free switching. In fragment-free switching, the switch stores the first 64 bytes of frame before forwarding. Memory buffering on switches. Port-based memory buffering. In port-based memory buffering, frames are stored in queues that are linked to specific incoming and outgoing ports. Memory buffering on switches. Shared memory buffering. Shared memory buffering deposits all frames into a common memory buffer that all the ports on the switch share. The amount of buffer memory required by a port is dynamically allocated. Duplex and speed settings. There are two types of duplex settings used for communication in the Ethernet network: half duplex and full duplex. Full duplex, both ends of the connection can send and receive simultaneously. Half duplex, only one end of connection can send at a time. Auto MDIX. When the Auto MDIX feature is enabled, the switch detects the type of cable attached to the port and configures the interfaces accordingly. Therefore, you can use either the crossover or straight-to cable for connections to a copper and over 100 over 1000 port on a switch, regardless of the type of device and the other end of the connection. Destination on the same network, there are two primary addresses assigned to the device or the Ethernet LAN. Physical address, the MAC address used for Ethernet NIC communications on the same network. Logical address, the IP address used to send packet original source defined on destination. Destination on same network, the layer 2 Ethernet frame consists of destination MAC address. This MAC address of the file server's Ethernet NIC. source MAC address. This is the MAC address of the PCA's Ethernet NIC. The layer 3 IP packet contains source IP address. This is the IP address of the original source PCA. Destination IP address. This is the IP address of the final destination, the file server. Destination remote network. Where the destination IP address is on a remote network, the destination MAC address will be the address of the host default gateway. Router's NIC is introduction to ARP. Recall that every device with an IP address on an Ethernet network has an Ethernet MAC address. Where the device sends an Ethernet frame, it contains these two addresses: destination MAC address, the MAC address of the Ethernet NIC, which will be either the MAC address of the final destination device or the router. Source MAC address, the MAC address of the sender's Ethernet NIC. Resolving IPv4 addresses to MAC addresses. When a packet is sent to a data link layer to be encapsulated in the Ethernet frame, the device refers to the table in its memory and find the MAC address that is mapped to the IPv4 address. If the packet's destination IPv4 address is on the same network as the source IPv4 address, the device will search the ARP table for the destination IP address. If the destination IPv4 address is on the different network that the source IPv4 address, the device will search for the ARP table for the IPv4 address of the default gateway. Removing entries from the ARP table commands may be used to manually remove all or some of the entries in the ARP table. After an entry has been removed, the process for sending in an ARP request, receiving an ARP reply must be occur again. Enter the map of the ARP table. ARP broadcast as broadcast frame. The ARP request is received and processed by every device on the local network. ARP spoofing. The use of ARP can lead to the potential security risk known as the ARP spoofing or ARP poisoning. This is a technique used by attacker to reply the ARP request for an IPv4 address belonging to another device, such as a default gateway. So that's it for my summary of chapter 5. That's all, and thanks for watching.